Well, in the previous lecture, we used DFS on trees, but today we move on to graphs. The most important difference is this. Graphs contain cycles, like this, or over here. And so, because of this kind of cycle, DFS without protection can easily fall into infinite recursion. And so, that's why in graphs DFS, we must use a visited array over here. So just so you know, just like the pass array in 3DFS, we mark the starting node as visited in main function before calling DFS. This is not optional. This is mandatory in graph traversal. I'm gonna write down the basic code first. I'm gonna name the function as DFS, and the starting node is 0. And like I said before, we need to mark the starting node as visited before calling the DFS. And so we need a visited array. We have 4 nodes, 4 by 4. Well, node 0 is connected with node 1, and node 1 is connected with node 2 and 3. And node 2 is connected with node 0, and lastly, node 3 is connected with node 0 and 2. There we go. I'm gonna print out the now value whenever we call DFS function. So, well, I'm gonna skim through 4 times using for loops. I'm gonna name it I as next to make this code more readable. And if map now next is 0, which means that we don't have the possible pass in the graph structure, we need to skip this part. And if visited next is set, we need to continue. Well, to prevent the cycle, I mean. Otherwise, I'm gonna set the visited array. And then I'm gonna call the DFS. Well, the reason why I don't erase the visited array in this case, well, we're gonna visit each node exactly once, so that's why we must not clear the visited array when the DFS function returns over here. So if I execute this file, 0, 1, 2, 3. So 0, 1, 2, and then this pass is the cycle, so we don't take this pass. And then we come back to node 1, and then we take this pass. So that's why the order of the now value is 0, 1, 2, 3, like this. And then, you know, if we erase the visited array when we come back from the DFS, well, this single line changes everything. Now we are no longer visiting each node once. We are exploring every possible pass because of this code. So remember this rule. If visited is not reset, we explore nodes. But if visited is reset, we explore paths, every possible path. So if I execute this file, it says 0, 1, 2, 3, and 2. Well, starting node is here. So 0, 1, 2, and this is cycle, so we don't take this pass, and we come back. And we go the node 3 over here. And then we don't take this pass as well because it's the cycle over here. And then we take this pass. So that's why it says 0, 1, 2, 3, and 2. So this is how we explore every possible path by adding this one code. Well, if we want to change this code into the adjacent list, we don't need the map array in this case, and we need the vector integer type with a list. We have 4 nodes, and we need to change over here. And we don't need this code as well. A list now I, and we need to initialize the A list as well. So node 0 is connected with node 1. Node 1 is connected with node 2. Node 2 is connected with node 1 is connected with node 2 and 3. And node 2 is connected with node 0. Lastly, node 3 is connected with 0 and 2. And if I execute this file, well, the result of this code is exactly same compared to the previous example using the adjacent matrix. Well, DFS can also accumulate values, and so such as distance or cost. Each recursive call carries the current sum value. So when we reach the destination node from the starting node, we process the result in this kind of example. And so by combining the FS with backtracking, we can find all past costs and minimum cost and maximum cost. So in this last example for today, we're gonna get those values. Well, I'm gonna write down the basic code first. Well, in this case, I'll name the recursive function as a DFS, and we need the source and some parameter. Before we jump into DFS function, we need to mark the starting node as visited. Well, we have 5 nodes and 5 by 5 to make the adjacent matrix. And so node 0 is connected with node 1 to 3, 3, 5, 4, 0. And node 1 is connected with node 2, 8, 0, 0. And node 2 is connected with node 1 and node 3 and 4. So 7, 1. And node 3 is connected with node 0 with 4 and node 4 with 10. And node 4 is connected with node 1 with 2 and with node 2 with the cost of 1 and 0 and 0. There we go. And we need the maximum value as well to update the cost. We need the minimum cost as well to update the minimum sum value. I'm gonna make the DFS. If now reach destination node, then I'm gonna print out all the possible sum value, and then I'm gonna update the minimum and maximum value for sum. So if sum is greater than maximum value, then I'm gonna update the maximum value. If minimum value is greater than sum, I'm gonna update the minimum value like this. And to make this code faster, I'm gonna return it right away when we reach the destination node. We have 5 possible nodes. If we reach map, well, I'm gonna name I as next to make this code more readable. And if map now next is 0, we need to skip it. If we reach, well, if visited next is set already, we need to skip it. Otherwise, I'm gonna mark the visited array like this. Let's dive into the DFS function. I'm gonna accumulate the sum value like this. Now, next. There we go. And then when we come back, I'm gonna erase the visited array because we are exploring every possible path. And so I'm gonna print out the maximum and minimum value. There we go. Well, I'm gonna execute this file. And so if I type in 0, 2, 3, it's gonna be 18 and 12 and 4. Well, if you take a look at this structure, well, you can see that starting from 0 and ends at node 3, there is the minimum path with 4, and this is the medium value, which is 12, and the maximum value would be like this, and it's going to be 18. So this is how it goes. And let's see one more. 1, 4. Well, this is pretty simple, pretty obvious, I mean. Well, starting from node 1 and node 4, well, the minimum pass would be 9, like this, and the maximum pass would be goes like this, which is 25. Well, let's change this code into the code using the adjacent list. So we need the vector. We don't need this variable anymore. Instead of that, we need the vector with the type of node, which will be customized by us. Well, in this node, we contain the number of the node and the weight. And so, well, this must be node type, and a list now size. And we don't need this code anymore. And this must be a little bit different, so I'm gonna throw in this parameter later. And so let's initialize the a list first. So node 0 is connected with node 1, 2, 3, and so 1 with price 3, 2 with weight 5, and 3 with weight 4. There we go. And a list 1. Node 1 is connected with node 2 with the weight 2. Weight 8, I mean. So node 2 is connected with node 1, node 3, and node 4. There we go. alias 3. Node 3 is connected with 0 and 4. Node 4 is connected with node 1 and 2. There we go. And so, well, the rest of them is all same, but the type of the variable next is different. So instead of throwing in the next directly, we need to throw in next n in this case. And we need to add the next weight with the current sum value. And so if I execute this file and throw in 0 to 3 or 1 to 4, well, the result of the code is exactly same compared to the previous one. And so this is all about today's video, and I hope you find it very useful through this video. Well, thanks for watching, and see you on my next video. Bye guys.